Hello, my fellow mad scientists, and welcome to today's lesson. Today we have an organic chemistry question which involves an addition across a double bond. Go ahead and pause the video and see if you can decide what the final product is on your own. So let's begin. We're going to start by drawing our alkene over here, which in this case is butene, and we're reacting that with bromine, right? So it's two bromine molecules bonded together. So the most important thing to remember when doing organic chemistry reactions is when you look at bonds, you want to remember that there are electrons located in those bonds. Each bond is 2 electrons. And during reactions, it's the electrons that you're moving about, right? So here in our alkene, those electrons are the negative charge that will act as the nucleophile. So we draw our first reaction arrow from that double bond to one of the bromines, right? That's where the nucleophilic attack is happening with those electrons. This is then going to break the bond between the two bromine groups, kicking off the second bromine as a leaving group. So what this leads to is actually, in this case, a pretty unique intermediate where you have one bromine here that actually has these sort of partial bonds like this, a very unique transition state, and that one lone bromine that now has a negative charge because those electrons have been pushed over to him, right? So as a result, what you would now expect is that these electrons here are going to do the second part of the reaction. They actually do a backside attack, which is what we consider an SN2 mechanism. So we draw our next arrow going from the electrons to any site of attack here, and that's going to break the bond, right? And so the final thing that we would expect is going to be our butene. Now, because this is a backside attack of an SN2 mechanism, what you want to know is that this is drawn with an anti-addition, right? And so what that means is that our first bromo is on a wedge and our second is on a dash. Okay, so a lot of reactions might be syn, in which they would both be dash or both be wedge. But when you're doing an SN2, you want to know that in this case, they are actually anti to each other because the second is coming from the backside. Now you might go, oh, easy enough. I see what the answer is, but not so fast. Even though this is the correct mechanism, this is not actually the correct solution for the reaction. And that's because we didn't pay attention to our solvent. Now, in this case, our solvent is water. And so the way this reaction ends is actually a little different. We still have an SN2 mechanism, but what happens here is, in fact, it is a water molecule with electrons on the oxygen that are actually going to attack that carbon. Remember, this is a carbon, break the bond, that sort of transition state bond, and form our final product. It is still an anti-addition, so we can draw the bromine on a wedge. We can draw our water on a dash. Now, initially, it's going to be a water, but another water molecule is going to remove one of these hydrogens, right? This is going to happen, and so this is just kind of expected. And so as a result, that doesn't necessarily need to be drawn. And what can be drawn is the final product, which would just have a hydroxyl or alcohol group present, right? I just wanted to show you the quick step of where that second hydrogen goes. He's just removed by another water. Now you might stop and say, wait, why does this happen? Why doesn't the second bromine get a chance to attack? And why is it water that does the attacking? Well, let's do a quick picture, and it actually makes a lot more sense. So let's just say this is like a reaction beaker. And in here, you have your, little product, and you have your other bromine group, right, with his electron. And we would expect him to attack. However, in here, we have lots of water molecules. You have to remember that if this beaker is filled with water as the solvent and the other just reactants in the solution, the number of water molecules is going to be thousands to maybe million times more than the bromines that are present. And in this case, well, which one do you think is more likely to attack? One of those numerous waters, or do you think that single bromine is going to get the chance? Probably not. And that's why what ends up being our major product is actually here. This kind of reaction is what we call a halohydrin. So to write that out for you, halo because bromine is a halogen, and hydrin because we're using water, right? So like a hydration reaction. If water was not the solvent, then we would see this one. So if you just had the bromine gas, you would see this as your final answer. However, because water is a solvent, what we actually see as the final answer is the halohydrin product, right? In this case, because we're using bromine, this is a bromohydrin. If you were using chlorine gas, you'd have a chlorohydrin. So let's real quick recap on the basic things we want to know. We are using our double bond as the nucleophile, right? We are going to be adding a group to both ends of the double bond when we break it. We want to remember that this is an anti-addition. Anti-addition here. Okay? Addition. And we want to pay close attention to our solvent in this case. Something like that can be the difference between easy points on an exam. And I don't believe we're missing anything else. I do want to quickly show one more thing that can be important for anti-addition. So let's take a second to see what this would look like if we were using a ring, right? Let's just say, for example, we're using a cyclopentene, right? Then if you drew this ring and reacted it, well, you could draw it with wedges and dash. Whoops, too much there. And you could draw it with one on a wedge and one on a dash, right? Or the other way that you might see this drawn is just with one going up, so above the ring, and one going below or beneath the ring. The picture that you see might be a little clearer, but ultimately you want to make sure that both of them are not going above or both going below, because that would be a syn addition. And these reactions do not react via a syn mechanism. So thank you so much for joining us for today's lesson. I hope this was helpful. Be sure to like and subscribe, comment if you have any questions or extra information you'd like to add. If you'd like to see more free questions like this, go ahead and follow Course Correction on Instagram. The link's down in the description. I post free questions like this all the time for lots of subjects. If you're interested in some one-on-one tutoring, you can message me on Instagram, or you can just email me at the email down in the description and we can set something up. Or maybe you just have a couple questions you'd like to ask. Then keep your eyes open for Course Correction office hours sessions. You can stop by one of those sessions during an afternoon or an evening, and we'll do our best to go over those questions and figure out the correct answer. Thank you so much for joining us in today's lesson, and stay mad.